So next session will be introduction to Microsoft Seal. Kim Leiner is the lead of Microsoft Seal, the whole library project. He has done excellent work. And this talk will be more fun because he's going to show some live code demo. It's like the previous talk, just director's narrative of the movie. Now it's the real movie. Let's give him a welcome and let's start the session.
Great, thanks, Wei. Yeah, live coding, I'm not sure about that, but at least I'll show you complete code examples. You can see the code, there's a URL there, github.com/kimleine/bootcamp. If you go there, hopefully I made it public. If you go there and you look at the native/example/examples.cpp file, all of the code example that I'm using here is in that file. And there's 4 different branches, so I'm going to go through these in order. So I start from something very simple, that's the 1_naive. Then look at some different ways of making the code slightly better and explain a lot about Seal and homomorphic encryption and also probably refresh some of what Yongsoo said in the previous talk in the process. No. Well, of course, you've already heard about Seal here. What I like to say is that it's a production quality homomorphic encryption library in the sense that it's actually deployed already by some companies, and it's going to be deployed by more companies in the future. We put a lot of effort into the quality of the engineering. We put a lot of effort into the examples that come with the code, in the comments, in the code, in the header files. It's been developed since 2015, and it's very, very actively developed today. We're currently in version 3.4, and today what we're doing is we're trying to release patches really often. Whenever we see some important issue that should be fixed quickly, or someone makes a pull request or so that we think should be incorporated and released as quickly as possible, then it can be usually out in like the same day. It's MIT licensed, and well, there's the GitHub URL. Seal is developed in C++ 17, and it also comes with some C# components. Namely, it comes with .NET standard wrappers, so most of you probably are not very familiar with .NET, but originally when .NET was developed and Microsoft created this so-called .NET framework, which is a big library, it was only for Windows. But today there's a .NET standard, and there's a cross-platform implementation of the .NET standard called .NET Core. And there's other .NET implementations also, other .NET standard implementations also. So today C# is a cross-platform language. Seal itself works on Windows, Linux, and Mac OS, and Android, and all kinds of platforms. It's most of the library is written in standard C++ 17. So as soon as you have a C++ 17 or maybe a C++ 14 compiler, you can build it. Now, what we're going to discuss, what I'm going to discuss in this talk, is a specific task that I want to implement with Seal, and after that, see how we set up the parameters for the CKK scheme. You've kind of seen this already. You've seen code snippets, but I'm going to show you some complete code. I'm going to show you how we do encryption, how we do some computation, decryption. Then, going forward, we're going to discuss some of this vectorization batching that Yongsoo was talking about in the previous talk for CKKS. And then we look at optimizations. How can we make our existing implementation better? Because it just turns out that when people start using Seal or any homomorphic encryption library, they do these implementations and it kind of works, but it's like often really, really slow. It can be 100,000 times slower than what it could be if it was implemented better. So the performance differences can be really massive between a simple implementation versus a highly optimized implementation by someone who's really experienced in this. And of course, this makes a big difference when you want to scale up, when your computation is something that's supposed to run in the cloud, or it's supposed to serve 100 million users, or something like this. Right. So the specific task that I want to do is something that is related to what Arun talked about in his talk on the fish detection, namely just a dot product. Well, in fact, what Arun did, he had 21, I believe, dot products. It was a matrix vector multiplication. But here, I'm just going to do one single dot product. Sounds very simple. But of course, this is a very powerful computation. It's a very generically useful computation. And many applications of homomorphic encryption, in fact, can be just this, because it could be used for some, as a part of some bigger protocol, for example, involving multi-party computation or other techniques where you just want to do the linear algebra with homomorphic encryption. Or it could be a neural network evaluation where the linear layers have to involve a lot of matrix vector multiplications like this. There's two interesting cases. There's the encrypted dot encrypted, where you need to do a dot product of two encrypted vectors, and there's encrypted dot unencrypted. And then you run into other considerations too, like what are the inputs? Are they integers? Are they floating point numbers? And then there's the question of the scale. Are we talking about 10-dimensional, 1,000-dimensional, million-dimensional, or billion-dimensional maybe? So what I'm going to do is encrypted dot unencrypted. Although, to be clear, there isn't a huge difference between the first two. I'm going to do doubles, which means that I will use CKKS. And finally, well, I'm going to start with the 10. But the idea of this talk is to go all the way to the 1 million. At least explain how we can do that, how we can make it scalable. What is the motivation? This is very strongly motivated by Arun's presentation. In a client-server setting, you might want to do a private prediction with a linear model on the encrypted data by the server. The server might own some kind of model, linear model that they want to evaluate, for example. Or for whatever reason, you want to do some statistics on encrypted data. You want to compute some kind of weighted sum of values of data that you have. Or these statistical computations using homomorphic encryption are very, very useful. It's easy to do things like sums and averages and weight sums and correlations and things like that. Or you might just want to compute the length of an encrypted vector. Maybe you want to compute the total distance of some path. All right, so let's see. Setting up the parameters. Here's my mouse. Like I said, if you look at the GitHub page and you go here to native, this is where all of our C++ code is. So this is where the main library is. If you look at src, that's where C source code is. But we're going to look at the examples directory. And here, there's examples.cpp. And I'm just going to show you this file here. And there's a function called bootcamp demo. And this is the only function that I'm going to be modifying in this in my talk. So you can clone this code. I'm actually going to run this in Visual Studio. So here's my examples.cpp. It's kind of, can I make it a bit smaller? Made it bigger. Why is it getting bigger? Huh. It's getting bigger. Huh. Okay, maybe I use the, okay, that's so weird. When I press minus, it gets bigger. Anyway. So Can everyone see this well enough? Or should I make it bigger? People in the back row? It's good. Okay. It's kind of okay. Great. So so what we have in this file is that this function bootcamp demo, and then we scroll just down a little bit, and we have our main function here. And the main function is very simple. All it does is it prints the version of Seal. I guess there's no specific reason for printing it. I guess I forgot it there. And then it runs the bootcamp, calls the bootcamp demo function. And then it doesn't actually do anything because I wrote false here, and it returns. So all it does is it calls bootcamp demo. Now, dot product. In this setting, we have two parties. We have a client who encrypts data. They encrypt a vector, 10-dimensional vector. Then there's the server who evaluates the dot product and sends the result back. And the dot product is with some unencrypted value. So the server has the weights. The server has the kind of the weight vector. It computes the encrypted, unencrypted dot product. Okay, so the client starts by creating a vector of doubles, which is their input vector. So here is a 10-dimensional vector, 0, 0, 0.0, 1.1, 2.2, up to 9.9. To set the encryption parameters, you already kind of you already kind of saw this in previous code snippets. But what we do is we create this encryption parameters object, and we tell it that we want the scheme type to be CKKS. And this is because we want to do a double. We want to encrypt doubles. And now, how are these parameters selected? You kind of got some glimpse of this already. It's in fact quite a complex process. So typically when someone develops code using Seal or any homomorphic encryption library, it's a very iterative process. You start with something, it kind of works. Then you try to make it better. You go back and you try to make the parameters better. It's not that you instantly say, okay, here are the parameters that I need. In the future, hopefully, we're actually working on some compiler tools that can help the developers and users do stuff better and more easily. But currently, it's kind of a repetitive, iterative process. So we start with this lattice dimension called polymodules degree. We just set it to 8192. This is definitely going to be big enough for our simple dot product. It's definitely going to work. I need to call this set polymodules degree and set coef modulus. So coef modulus is this parameter q that Yongsu was talking about. And what this function did was, for a given lattice dimension, we give here bit lengths of 3 primes that we want to be in our coef modulus. So we're going to have a 50-bit prime, a 30-bit prime, and a 50-bit prime. And the last one of these primes, it's something called a special prime, and it doesn't. It's only used in some internal operations. In fact, it's not. It doesn't appear really in your view when you do encrypted computations. Now, how are these chosen? I'm going to get back to that. But let's just set them like this to begin with. Now, once the parameters are set, I need to create a Seal context. So Seal context does a bunch of pre-computations because, for example, these parameters need to be validated. Are these parameters set correctly? Are they set in a reasonable way? Polymodulus degree, for example, it has to be a power of 2. The lattice dimension has to be a power of 2. It can't be too big. It can't be too small. So it checks when you create this Seal context, it checks that everything is okay. We can print. We can check here that using this function or using this member variable of some member of the context, we can check that if the parameters were set actually correctly. And we just print true or false. Of course, it's going to print true because well, these parameters are valid. Like there was like was discussed in the previous talks, there's an upper bound for the coefficient modulus bit count. So the security level here really depends on the lattice dimension and on the sum of these bit counts. So if you increase the lattice dimension, it gets more secure. If you increase the total bit count here, it gets less secure. So for a fixed lattice dimension like 8192, there's like an upper bound for the total bit length that you can have. And if I would set here something like this, it would be insecure. And in fact, what would happen is that the parameters are valid would just print false, because the parameters would be insecure. It doesn't. Seal protects you from doing anything stupid, so it doesn't allow you to set insecure parameters. Although that check can be disabled. In some cases, it's desirable to disable that for whatever reasons. Okay, so that's that. And here, what we're doing here, we're printing the largest bit count that this particular lattice dimension supports. And here we're also printing our total bit count for the currently set parameters, which is going to be 130 in this case. Let me just see if I can run this. Anyway, so it's compiling and running. I set the scale. Youngsu talked a lot about the scale, this delta. I set it to be 2 to the 30. Let me show you the output. Actually, it ran it. So here's what happened. It says parameters are valid true. Maximum allowed coef modulus bit count for this polymodulus degree is 218. Currently set coef modulus is 130 bits. And then it does the computation, the encrypted computation, and then it does the same computation on unencrypted data. I'm going to come to that. And obviously those results match. Here we set the scale. And now to encrypt, to encode data for CKKS, we need to first set this CKKS encoder object. Very simple. And now I want to encrypt my numbers. So I'm going to create a vector of plaintext. And for each value in my inputs, so my inputs was the vector of doubles here. For each value there, I'm going to create a new plaintext. And I'm going to call encoder.encode that particular double with my scale 2 to the 30 and write it to the plaintext P that I created here. And then I will just move this plaintext that I just created, and I just encoded my value into that. I'm going to move it into the vector so it's placed there. Well, that's all great. Now, if you were following the previous talks, you know that there is this batching functionality where, in fact, you don't just encrypt or encode one number, you encode a whole vector of numbers. In fact, in this case, we would encode a vector of 4,096 values. But the version of the encode function, it only took one value, so there's some overload. There's like multiple overloads of this .encode function. There's like 10 different variants of it. Some of them take a single double. Some of them take a span. Some of them take a vector of values. And what happens is, if I give it just a single double, what it's going to do is it's going to replicate it into all of the 4,096 slots. So in reality, I'm not just encoding one value. I'm encoding a repeated vector of 4,096 copies of that value. In any case, I encode each of those into one plaintext. Per each of my inputs, I'm going to create one plaintext, and then I add it to my vector of plaintext, PTS. Now, to do encryption, I need a key generator. A key generator creates automatically a secret public key pair, so I can read those into SK and PK. I can create an encryptor. Encryptor uses the public key to encrypt. And to encrypt, well, I need to create a vector of ciphertexts. So I set that up here, and I go over all of my plain texts. For each plain text, I create a ciphertext. I call encryptor.encrypt plain text into ciphertext, and then I move the ciphertext into the vector. So that's it. And all I need to do now is I need to send this vector to the server, and I also need to send the encryption parameters to the server. That's easy enough. Actually, yeah, let me get to that serialization part a little bit later, if there's time. Now, so what happens? The server obtains the encryption parameters. The server deserializes them, and the server creates its own seal context object. But because, for simplicity, I wrote everything into one single function, I already have my seal context. I'm not going to create a new one. But now here's the server's vector of weights, or this is the plain text dot product multiplier. It's just some random values. Well, it doesn't look very random, but 2 minus 1, 2 minus 1, 2 minus 1, and so on. And I create the vector of plain text called weight PTS. And for each of the weights, I'm going to create a plain text. I'm going to encode, again, using the same scale, 2 to the 30. And I add my plain text, actually. I probably should have here move. Great. And then I'm ready to do the computation. So I need an evaluator. Evaluator is what allows us to do all of the encrypted computations. If you look at what all member functions we have for evaluator, there's things like add in place, add many, add plane in place, apply galore, complex conjugate, exponentiate, all kinds of things, multiply, negate, relinearize, rescale, rotate, square, sub, transform from entity, and so on. All kinds of things. Now, I'm going to loop over all of my ciphertext that I obtained from the client. And for each of them, I will do a multiply plain in place. So multiply plain means multiply a ciphertext with a plaintext. In place, of course, means that the CTSI is overwritten by the result. So I multiply CTSI with this plaintext, and then I do a rescale to next in place. So what happens here, to go back a little bit to Yongsoo's talk again, what happens is CTSI has a scale of 2 to the 30. Weight PTSI has a scale of 2 to the 30. I multiply those together, now I have a scale of 2 to the 60. But I don't need that much precision. Now I have all these extra bits of precision there. I don't need it, so let me just rescale it down. And what happens is when I do the rescale, if you look at my parameters here, remember the last prime was some kind of special prime, so we just completely ignore that. But so these two are the ones that you should look at. There's 50-bit prime, there's a 30-bit prime. When I rescale, it gets rid of the last one of these two, that's 30. So it kind of drops that prime from the encryption parameters, and it divides my plaintext by that prime. So that's a 30-bit prime. It's very close to 2 to the 30. And in effect, what happens is after this multiply plain in place, my scale was 2 to the 60. Now I do a rescale to next in place. It divides the plaintext by some prime that's close to 2 to the 30, and I end up with the scale that is close to 2 to the 30, although not exactly 2 to the 30. It's actually quite common that in these cases, I might want to maybe sort of renormalize the scale back to an exact value 2 to the 30, because after the rescale, the scale is not really going to be 2 to the 30. It's going to be 2 to the 60 divided by some 30-bit prime. But I might want to just change it like this. it creates some small amount of error in my result when I decrypt, but it makes it much easier when my scales are some powers of 2. Now, what do? I have done all the multiplications, plain text by ciphertext. I sum them up, and luckily, Seal just happens to have a function called add many. Of course, this function does nothing very magical. It just calls add many times. Well, so I give it a vector CTS, and it writes the result to CT result. And now, if I'm the server, I've completed this operation. I send this back to the client, and the client can decrypt. So the client decrypts by creating a decryptor, takes the seal context again and the secret key now. What I do, I create a plaintext result, and I simply call decryptor.decrypt, ciphertext, result plaintext, and I need to decode it. But as has already been explained, CKK always encodes vectors. It always encrypts vectors. So there isn't really such a thing as encrypting one single number or encoding one single number. So when I decode, I have to give it a vector destination where it's going to put my result. And I simply read the first component from that vector. In fact, all of those slots in the vector are going to have the same value in them. And that's because of how this overload of the encode function worked, that it replicated the value into all of the slots in the vectors. Funny enough, C++ has an inner product function, so it's very easy to compute the inner product, the dot product like this, and I can print it. And like you already saw, I ran this, and I get the same result from the encrypted and the unencrypted computation. So, right, it works, of course. So, any questions about this? Mm-hmm. It's not exactly the same, but up to a lot of precision, it is the same. So it just showed them to be the same. Yeah.
In this inner product function, what is the 0.0?
Oh, that's the starting point. So it's like multiply and accumulate, and it starts to accumulating from 0.0. Mm-hmm.
It sounds like the purpose of it is to allow sort of rescaling yourself after you do this
mm-hmm.
multiplication, but you also then have to enter the scale yourself later. Is there a reason that those two
mm-hmm.
numbers, like,
mm-hmm.
I guess, why not enter it once and use it twice? Like, why
mm-hmm.
enter it twice?
Yeah, good point. A good question.
Oh
yeah. So the question was because my scale is 2 to the 30, and it seems that the scale is specifically set to match the bit length of the second prime, which is 30 bits there. Then why do I need to enter this twice? Because shouldn't it be enough to just set it once, and then the scale would, for example, immediately know what it has to be? It's a really, really good point. I think. In many cases, that would work. But one challenge of designing APIs for homomorphic encryption is that often it really matters that you can squeeze out every possible bit of performance from the scheme, from the system. And you often end up in situations where you need to do some very complex or unexpected optimizations to really make it work as well as possible. And in these cases, you can end up in situations where, for some reason, you don't want those to be the same. There are many reasons why you wouldn't necessarily want them to be the same, but maybe in most simple applications, they should be. No, hold on.
Okay, can you explain a little bit more about the choice of those three numbers, the prime numbers, 50, the number of bits, 50, 30, and 50?
Yeah.
How do you set these, and why do I have 3 only? Why can't I have 4 or 2?
You could have. I could add one more. The only thing is that I can't exceed 218, I believe it was,
Okay.
bits total. So this should work. Now, so what's going on here is that, like I said, the last prime is what we call the special modulus, and typically the special modulus should be as big as the biggest of the other primes. So if I have a 50 and a 30-bit prime, the special modulus would ideally be 50 bits. No more and no less. If it's less, it still works fine. You just get some more error in some operations, which might be okay. Like in some cases you might want to push down that last prime. You get some more error in some computations, but you get a smaller coef modulus, which might allow you to actually jump to a smaller polymodulus degree altogether, or something like this. There's a lot of reasons why it might not have to be exactly as big as the biggest one, but it's a good rule of thumb that you should always start thinking of it as big as the biggest of the other ones. Now, for these first two, the way you should think of it is that so when you have a floating point input, what really happens here is that that floating point input is it's scaled up to an integer, and it's scaled up in this case, of course, by the scale 2 to the 30. And this scaling is really important because well, I don't have a nice graphic here to demonstrate this, but what happens is that in encryption we introduce some noise to the low order bits of these polynomial coefficients, and if we haven't moved our message kind of to high enough away from the lowest bits, low order bits, then that noise that we get from encryption is going to mess up your message. That's why we need the scale to be big enough. It has to be, let's say, usually at least 20 bits. Maybe it can be a little bit, maybe around 20 bits I would say is pretty much the minimum. It can go higher, in which case your message is further away from the noise that comes in the beginning. Now that explains why my scale is, kind of answers why my scale is 2 to the 30. It's just a choice that I made. It could be 2 to the 25, it could be 2 to the 40. Those all would work fine. I just chose 2 to the 30 because it's big enough, protects my message, I don't get any error from the encryption. And that choice then impacted my choice of the middle prime there, this 30, because I wanted to show the rescaling. And in most cases, again, what you want to do is you want to have your middle primes, so everything after this, after the first one, you kind of want to be equal to your scale in most cases, because that allows you to stabilize your scales. You multiply two things, the scale doubles, you rescale by one of these primes, and it kind of resets the scale. And then you can do this type of scale normalization still, which exactly sets your scale to be 2 to the 30 again. You get some small error from this brute force thing, but that's okay. And so that's what I just wanted to demonstrate the rescale. That's what influenced by, and I wanted to demonstrate this scale normalization, scale stabilization technique. So that's why 30. And finally, this 50. So now what happens? I did that multiply. So I had a 30-bit input and a 30-bit plaintext, 30-bit scale in my ciphertext, 30-bit scale in my plaintext. Multiply those, 60-bit scale. So now my plaintext is really far from the low order bits. And now I scale it down by 30 bits. So I'm going to be back at 30 bits scale. And but now what has happened is I have actually gotten rid of this 30-bit prime completely. So it's gone from my encryption parameters. So my encryption parameters, after that rescale, they only contain that 50-bit prime. This is modulo switching. And this means that now I have that 30-bit scale. My plaintext is kind of contained inside a 50-bit prime with the 30-bit scale. So there's only 20 bits above the scale. So there isn't that much room for the kind of the integer part of the plaintext anymore. There's only 20 bits room for that, which is not very much. But it's enough for this example. So ideally, maybe, you know, if I would want there to be more room for the integer part, maybe this should be 60. 60 is the biggest prime size that you can have in Seal. So this is 50 because it's a demonstration, and I just decided that, you know, that's the first thing that came to my mind.
So if the result is bigger than 2 to the power of, if the result of bigger than 2 to the power of 20, in this case, it won't work.
That's correct.
Okay.
So I had a few questions. One is about the line which you had there, like setting the scale exactly to be 2 to the power 30. Mm-hmm. What's the benefit there, as opposed to a scale which is approximate?
Okay, so what's the benefit of this sort of pattern, where I do a multiply, rescale, and then set the scale like this? Mm-hmm. The benefit is that, suppose I have I do two products, A times B, C times D, and then I want to sum those two. Mm-hmm. It's a bad example.
Or maybe, yeah, you want to take the product of those two.
Bad example. So say something simpler. I want to compute A times B, and then I want to add a ciphertext C to that. Mm-hmm. Okay? But now, suppose my ciphertext C has a scale of 2 to the 30. My A and B have scale 2 to the 30. So I multiply those. I get scale of 60. I do rescale. But now my scale is not 2 to the 30. It's 2 to the 60 divided by my 30-bit prime. Mm-hmm. But that's not 2 to the 30. Yeah. So what ends up happening if I try to do the add, Seal is going to throw a runtime error, because you're trying to add two things with different scales, which doesn't make sense. Like, you're probably doing something wrong. Well, in this case, actually, you're not doing anything wrong. We just need to make sure that the scales are the same so that it doesn't complain.
I see.
So that's why it's important to set the scale by brute force to be exactly to the 30, so I can do that.
So actually, you can also retrieve the scale by calling just ctsi.scale. That function also can return you the exact scale after the calculation, after rescaling. You can see that it's not the power of 2, but it's really close to the power of 2. And you can either use that value to set up the other ciphertext, or as Kim did here, use the power of 2, which is much easier. And I think you still have a question.
I see. So as a library, it's not, even though like both of them are close to 30, so the computation would still be almost equally correct in terms of the relative error being the same, but it's sort of just for the library design that you want it to be controlled by the user, that every time you do the computation, you have to do this.
It should be controlled by the user. There's also cases where you want to perform a sort of division by just changing the scale. Mm-hmm. And of course, that's not a real, or a multiplication or a division. You can just achieve that by changing the scale. Then Seal thinks that, well, the scale is this, and when you decrypt and you decode, effectively you've performed some multiplication or addition or division, depending on how you change the scale. Okay. So in some cases, you really want to have concrete control over the scale, and you might want to do hacks like that.
Okay. And then one other question is about, so we use the ciphertext is actually stored using CRT, and so you had these different primes. And when you actually divide, do you effectively throw away one component, like one CRT component?
Yeah, sure.
That's okay. So effectively, the size really keeps going down.
The size keeps going down, yes.
I
so
see.
when you do rescale, we literally throw away components of the ciphertext. We get rid of part of it, and the size the physical size gets smaller, yes.
I see. And one final thing, so if we use this set of 50, 30, and 50, we can actually use a ciphertext modulus which is lower than 218, right? Like we can go to something smaller.
It could be something other than what I had there, yeah.
Okay.
As long as it's less than 218.
18,
And if I want to have a bigger ciphertext modulus, then I need to increase my polymodulus degree, my lattice dimension.
Okay. Thank you.
Oh, hold on.
Actually, he's been
Oh.
waiting.
So going back again to the 50, 30, 50, you mentioned that the more primes you put in, as long as it makes it less than the 218, the less secure it becomes. And
That's true, yeah.
I know it was said earlier that that's work in progress to make that as part of SEAL, but is there any indication in like the current code how we'd be able to see whether the primes we're putting in are as in how
it
by
affects
how
the
much
security?
it's becoming, affecting the security?
So the reason SEAL enforces that bound 218 in this case is because we want to ensure that there's at least 128 bits of security. So indeed, if I only have one prime here, like this, it's going to be like, I don't know, 1,000 bits of security. But why would anyone want that? You're doing something silly in this case because you have an unreasonably high security level, which doesn't really give you anything. You could just as well decrease your polymodulus degree to get to kind of lower the security level, but your lattice dimension gets smaller, you get better efficiency. Now, is there some concrete way of showing what the security level is, what exactly the security level is? The answer is no. Okay. It's not, unfortunately, that easy. The way these bounds, like the 218, is estimated is using this LWE estimator tool. Right? And these are discussed in the homomorphicencryption.org meetings and things like this.
Yeah, so there's just nothing kind of that would in the code
it's
in
not
SEAL
that
would,
simple,
okay.
unfortunately. No. What we have is these bounds.
Yeah,
and what
that's
you
fine.
can do is when you create your SEAL context, if you look at this, whatever. So if you look at this, the last parameter there is something called the sec level type, the security level. So you can give it a different security level. You can say, well, I want a sec level type of 192 bits, and now it doesn't allow you to even go to 218. Maybe it's something like 170. I don't know, but it caps it at some lower level so that we get 192 bits of security.
Right. Okay. Yeah, that's fine. Thank you.
So this is maybe kind of going more to the direction of encrypted.encrypted, but right now we're not using the batched encoder. We're like making a ciphertext for each and then multiplying.
That's right, yeah.
So like, how would the performance compare to like if I did a batched encoding and then I multiplied and then I like did a bunch of rotate adds?
Let's move forward with the talk so that you'll see that.
Okay.
All right. So, let's see my slides. Well, we did this stuff, and the next topic is vectorization/batching. Because now you should indeed ask, so what is the cost of this? And I can tell you the cost is huge. This is we did this for a 10-dimensional dot product, and but what's going on there is that because we're not using vectorization, we're not using batching, we have a 4096 times duplication of data and computation for no reason at all, really. Of course, it works for a 10-dimensional case, but this is definitely not scalable to 1,000,000 dimensions, and it would be terrible even for a 1,000-dimensional example. This is certainly this approach that I just showed you is certainly not something that we could have done with our own project, because we need pretty good latency there and pretty small communication cost. So 1,000-dimensional. So what we do is we want to use batching to put all those 1,000 things into one single plain text. Then we want to encrypt that, and then we want to do just one single SIMD multiplication to do all of the 1,000 multiplications. But now there's a challenge, which is how do you compute the sum? Because you end up in a situation where in the first slot you have the product of A1 times B1. In the next one you have A2 times B2 and so on. And how do we sum those? Of course, there's some naive solutions, which is that you can just send this back to the client, and the client could compute the sum on unencrypted data. That's one way. But what if we really want to do it on encrypted data, which makes a lot of sense? One technique would be to rotate 1,000 times and accumulate everything into the first slot. Unfortunately, rotating 1,000 times is not really necessarily what you want to do. It's kind of slow. I didn't show you anything about rotations yet, but there are these Galois keys that we need to create. It's some kind of public key that we need to give to the server, and the server uses that Galois key to do an encrypted rotation of the vector. So of course what that means is that when you have an encrypted vector A, B, C, D, it's going to do like a cyclic rotation in encrypted form. Now, the better way to do this is as follows. Here's an example. Here's an 8-dimensional vector, and I want to sum these slots. So what do? I rotate it by one step. So I rotate that way by one step, and then I add. Then I rotate the result by 2 steps, and I add. Rotate by 4 steps, add, and, well, kind of miraculously, I have now summed up the values in all of the slots. So in fact, I only need to do log n over 2 many rotations. N is the lattice dimension here. And in this case, n is, if this is CKKS, then n is 16. My lattice dimension is 16. My vector size is half of that. Oh, sorry. My n is 16. Okay. So that's how it goes. So let's implement it. In fact, what I just did was I skipped one of my branches. So instead of okay, so I'm just gonna get rid of my changes. So let's check out. It's the branch called 3 rotations. So let's, oh, that one. Great. Okay, I made some other changes to this branch too. I added a stopwatch, which is a really simple stopwatch. When you construct it, you give it the name, and the constructor records the current high-resolution clock time, and the destructor records the current clock time, and it computes the difference of the time points, and it prints the duration and the name of the timer. So this is not very, okay, it is what it is. At least it gives us some indication of what the running times are. So, bootcamp demo. We have 1,000-dimensional vectors. I have a size t called dimension, which is 1,000. And I create my vector of inputs. Like a good citizen, I first reserve my array size to dimension so that I don't have to do any costly reallocations in my vector pushbacks. Anyway, I push these values in. So what are these values going to be? It's going to be 0.0, 1.001, 2.002, 3.003, and so on, all the way to 999. And CKKS. It seems I've switched this to 60. So why have I switched it to 60? It's because now I'm actually going to get a pretty big result. My 50 wasn't enough anymore. After rescale, I had only 20 bits left, 20 bits kind of above my scale, up to that 50 bits. So if this prime would be 50 bits, I would get an incorrect result because my result is overflowing the coef modulus itself. The coef modulus is only 50 bits, and my scale is 30 bits, so I only have 20 bits there, which is not enough for my result, which is now much bigger than in the previous example. So that's why I just put it to 60. And it works. Note also that 60 is, like I said, the biggest prime bit count that you can have. So I couldn't put this to be 70. There's ways of dealing with that, but something that I could always do is I could just add an extra prime there, and now I have much more room for my data if it ever comes to that. All of this is the same. Create the seal context, set the scale, create the encoder, but now I'm doing something much simpler. I create just one plaintext. It says create vector of plaintext, which is a lie. I'm just creating one single plaintext. And I call encoder.encode. I give it the vector of inputs, so it's a vector of doubles. I give it the scale. I give it the destination plaintext, and it's all encoded in one go. Key generator again, nothing new there. But now, something that I do need to do is I need to create these Galois keys, because otherwise I can't do rotations. And I need to give the Galois keys to the server. For example, I add this stopwatch here to show you the Galois key creation time, because it's kind of substantial. It takes some time to create this, especially for bigger parameters. I create an encryptor, and I do an encryption. I also print the encryption time. Note again, there's only one single encryption that's happening now. Unlike in the previous example, I had to do 10 encryptions. Now I do only one. But I'm encrypting 1,000 values. To show you concretely the size of my ciphertext, I do some serialization, and also to show you serialization. This is how I would really communicate the ciphertext and all of my data to the server. I would create an output file stream, and I save my ciphertext to a file called test.ct. Make sure to have iOS binary there. You can't believe how many people don't have that there, including myself. And then you get some, it's going to crash when you try to load it or something like this, because it does line-end conversions. C++. Anyway, ct.save, and I just give it the output file stream, and it works. And same, I save my Galois keys just to demonstrate the size of these objects to you. And the Galois keys go to test.calc. Oops, did not mean to do that. Okay, so now we send this vector. Not vector, because I only have one ciphertext now. So I send that one ciphertext to the server. And actually, I should also probably serialize my encryption parameters. I could do that, but being lazy, I'm not going to do that. The encryption parameters are very minimal in size, as you can imagine. Okay, server. Server, again, has a 1,000-dimensional weight vector now. And what I'm going to do is I just replicate that same pattern, -1, 2, -1, 2, -1, 2. To all of the 1,000 dimensions. And I create one single vector of doubles. I encode that one with the same scale 2 to the 30. It goes to weight PT, weight plaintext. And again, I print the encoding time. I create an evaluator. And now I do one single multiply plane in place. And this does the SIMD multiplication, and then I do a rescale to next in place. Why not? And finally, I need to sum these values because now I have a huge vector. I want to truly compute the dot product, so I need to do the sum using this logarithmic rotation trick that I just showed you. It's here. You can look at the code and verify that that's correct. Well, maybe I should say something more about this. So the way to do a rotation in CKKS, I need to call rotate vector. It rotates the vector it rotates the ciphertext CT by I steps. This is an int, so it could be in either direction, plus or minus. And I need to give it the Galois keys, and here's the destination. There's also a rotate vector in place, but I need to write it to a temporary variable because I then want to accumulate it to my ciphertext. So I do an add in place. Well, once I've done that, now the ciphertext CT, it has in every slot it has the same value, which should be the value of the dot product. So I send it back to the client, who sets up the decryptor, decrypts, decodes. Here is decoding. Decoding goes to some vector of doubles, and all I need to do is read the first element from that. And if all these C++ gods are smiling on us, then it should print matching results. It's kind of slow to start this because Windows insists of doing like a virus malware check when I run seal. Anyway, result 999999, true result 999999. Cool. And you can see these times. Some interesting. Can I make this? I'm not even going to try. I hope you can see it. Oh, that works. So you can see that the Galois keys creation time was 218 milliseconds. So which is a lot compared to all of the other things. So, for example, encryption time is only 5 milliseconds, encoding time 1 millisecond, multiply and rescale 1 millisecond. Summing the slots takes a little bit longer, 16 milliseconds. Decryption time, it's not even a millisecond. Great. Any questions about this one?
So the way you have your parameter set, I guess I want to make sure I understand that. So the encoding, like you do an FFT over
In encoding?
Yeah. So like you have.
Mm-hmm.
Do you need to wrap for the negative values that are output by the encoding? And so like would that give you like effectively 15 bits here of space?
I have to say I'm not sure what you mean.
So
the
like
encoding is. Are you familiar with the CKKS encoding?
yeah. I mean, so does it output like negative values? And so to encode the negative values, you need to like wrap, right? Or
Yes, that's true. So everything is represented then modulo Q.
Right.
Right.
Yeah. And so that gives you like 15 bits of space, right? I mean, like 15 bits of like magnitude.
I'm not sure. I don't understand what you mean.
So like you have a 30-bit scaling factor,
Mm-hmm.
and then but your top modulus when you go to decrypt is 60 bits.
True.
And,
Okay,
and
so
you
I have basically 30 bits room for my integer part. Of course, there is then some. I mean, there's some sort of like FFT that has to happen there. Yeah.
And so you have like 30 bits of total space, and then like 15 bits, and because you have to like wrap for the negative, that's like, does that mean that you only have 15 bits of actual space, or?
No. The sign is only 1 bit. There is 30 bits of space basically, or.
Okay.
29. Yeah. So you can't. Unfortunately. This is not quite the full story. There's all kinds of errors coming from this FFT. Like I said, the low order bits are being messed up by these encodings and things like that, and encryption. So somehow, like, you can't say exactly that, okay, if my scale is something, then there's exactly this much precision. It's not, unfortunately, quite that simple. It is possible to create some maybe average or worst case estimates for like the precision that you get, but currently such a thing is not implemented in SEAL.
Okay.
So I've just looked at the evaluator, and something like this sum of all the slots in the plain text or in the ciphertext is not a function that's implemented there, so, because it seems like this is kind of something you need a lot. So is there like a standard library of such functions, or is that not available at this time?
Yeah, truly, I'm not sure why it's not implemented. So, so in some cases, I think there are some situations where you might not want to sum like all of the slots. If you use the BFV scheme, the situation is a little bit different for the BFV scheme also, which means that the API would have to be maybe a little bit different for that one. So that's why we haven't added it to the evaluator, because it kind of it's not totally obvious what you want it to be. In most cases, it's probably exactly this that you want it to be, but not always. And it's pretty easy to create it, but I would say that going forward, hopefully, when we have some developer tools, some better, maybe some compiler help for writing SEAL code, then maybe a developer really doesn't need to understand anything about it, and maybe it really doesn't need to be in the SEAL API, because there's some tool that can help do that.
Yeah, and in some cases, we still do some crazy things, like say, I use half of the slots, first half of slots to put meaningful data that I want to sum up. The other half of the slots, I want to use it for other purpose. And then that API wouldn't work on this because I try to sum half of the slots. So we are giving out some flexibility here and haven't come up with like a good solution for general API yet.
Okay, so here's, the font is kind of small. I'm not even going to try to increase it, but there's a test.ct, and you can see it's 205 kilobytes. So my 1,000-dimensional vector is encrypted into it's really 4,096-dimensional vector, but I only use 1,000 of the slots. It's encrypted into 205 kilobytes. The Galois keys are substantially larger. It's 16 megabytes almost. So let's see my slide. The size of Galois keys can often, let's say sometimes be an issue, but it's often an issue. It's 16 megabytes here, but if you use much larger parameters, the Galois keys can be huge. And in these cases, it's really important that you have some mechanism for caching them. You don't want to have to necessarily resend them from the client to the server every single time you do any computation. I did want to talk about some of these optimization. I'm not sure if I don't really have time, but for example, one of the things that we can do is make these Galois keys smaller as follows. By default, if you create Galois keys the way I did it, key generator keygen.Galois keys, open, close parenthesis, it creates Galois keys that allow you to do any rotation. Any rotation. But sometimes you don't need to do just any rotation. Sometimes you need to only do like a specific rotation or a set of specific rotations. And what you can always do is you can create Galois keys for those particular rotations. So when you call that keygen.Galois keys, you can give it a vector of integers that tells exactly what step counts you want to rotate by. Now, in reality, what happens when it creates Galois keys for any rotation, it creates logarithmically many keys for rotations in both directions. 1 step, 2 step, 4 steps, 8 steps, and so on in one direction, and same for the other direction. So this means that now, if you say that, okay, I want to do a rotation by like 5, 6, 7 steps, it's going to get an optimal combination of these back and forth rotations by power of 2 steps to get to your desired rotation as quickly as possible. But for example, in this demo, I only needed rotations in one direction, not in the other direction at all. So my Galois keys are twice the size that they need to be. I only need rotations by 1, 2, 4, 8, 16, 32, and so on, up to, I guess, 2048. So in fact, this 16 can immediately be halved if I create my Galois keys in a more intelligent way. Now, some other thoughts about optimization. My coef modulus was 60, 30, 60, but maybe that's too large. I can, in fact, decrease it to this one. I can decrease my scale to 2 to the 20, and it works fine. And I get enough accuracy. So that's something. One thing that's really important to do is to enable, since SEAL 3.5, we've supported, SEAL 3.4, sorry, we've supported zlib compression. So that means that when you have a ciphertext and you save it, it automatically runs it through zlib to compress it. Now you should ask, okay, something is really fishy there, because if you have a ciphertext, you shouldn't be able to compress it because it should be uniformly random. But the thing is that because in SEAL we use things like 20-bit primes, and it's serialized as, or it's saved as a, well, even in memory, it's represented as a 64-bit word. So there's 40 bits of zeros. And now when you serialize this stuff, you're going to have some data there which is mostly zeros. And certainly it would be possible to do some clever bit shuffling thing to make it all work, but it's such a headache and pain that it's best just to compress those zeros away with zlib. So it's really important that this is enabled. And it allows some other optimizations too, which I don't have time to discuss, but they are mentioned in the slides and they are demonstrated in the code, I believe. Actually, my seal that I used here, it already had zlib enabled. And if you look at the readme.md for seal, it explains how to enable this stuff for Windows and Mac and Linux. But that's actually more important than one might imagine. So some other thoughts that I had. We could just not do the rescaling. That's not really a reason to do a rescaling in this case, because I only do one multiplication. If I do the rescaling, then the communication back from the client, from the server to the client is a little bit smaller because I get rid of one of those primes. But on the other hand, if I get rid of that if I don't do that rescaling, then I might be able to decrease my coef modulus more, because I don't need my first prime to be so big. See, if my coef modulus was like 40, 30, 40, do that multiplication, I have a 60-bit scale, and if I would now mod switch away or rescale by that 30, I would be at the 30 bits, but now my first prime is only 40 bits, so I would only have 10 bits room there for the integer part of my message, which is not enough. But if I don't rescale, I have a 60-bit scale after the multiplication, and I have a 70-bit. Oh, sorry, I'm using a 20-bit scale here. Yeah, 20-bit scale. So I have a 40-bit scale after the multiplication, and then I have 70 bits total of coef modulus, and that's enough to hold a lot of integer part. Okay. So then, in fact, since I'm going to so small, I'm thinking now of much smaller coef modulus. So in fact, maybe I can lower the polymodulus degree to 4096. In fact, this is possible. If you look at my optimizations branch, you'll see that this truly works. In this case, though, the maximal coef modulus bit count is 109, not 218, so it's half of that. And some stuff that I tried coef modulus 40, 30, 39, works fine. But actually, I can even do better by using kind of more even selection, 37, 37, 35, because if you think of what is 30 plus 40, that's 70, versus 37 plus 37 is 74. So I have, in fact, 4 bits more room in the second choice. So it's a little bit better, maybe. But all in all, after these optimizations, my ciphertext size is now 92 kilobytes, so that's gone down from 218 kilobytes to 92. And my Galois key size is not 60 megabytes, it's like 6 megabytes. So I can improve it further, like I mentioned. I don't have to create the Galois keys in both directions, I only create it in one direction. So now the size is halved, 2,900, the size goes to 1,490 kilobytes. What am I saying? Sorry, the size goes down to 2,975 kilobytes, and then there is a further trick that can be done. If you have zlib enabled, you can create half of the Galois key from a seed, which means that I don't have to actually serialize half of the Galois keys at all. Again, this is some new trick in Seal 3.4, and you need zlib enabled, but I can actually cut my Galois key size by half, again, using this. So I can cut my Galois key size to just 1.5 megabytes. And you might also have noticed that I don't actually use the public key really at all. So Seal 3.4 allows you to do symmetric key encryption, in which case half of the ciphertext can come from a seed. So I don't have to send half of the ciphertext at all to the server, which decreases my communication size and my ciphertext size. So in fact, I can halve my ciphertext size to 46 kilobytes. And now my sizes are really, really much smaller than before. So I went down from 205 or some 200 kilobytes to 46 kilobytes, and my Galois key size from 60 megabytes to 1.5 megabytes. And finally, you might ask, okay, well, is this now enough to do a million-dimensional dot product? What I would have to do is I take my million-dimensional inputs, I put them into many vectors. There's like 400-something plain texts. And I need to do the CKKS batching for each of these 400-something vectors. And then I need to do my multiplied plane on the server for each of these separately. But everything is parallelizable, as that par there suggests. Everything is parallelizable. What I need to do, after the server has computed all these 400-something multiplications, I need to add those together. I do one single sum slots, and now I have the million-dimensional sum dot product value in all of the slots. And this actually really works. What we get here is the ciphertext size is about 23 megabytes, and rough estimate on one thread, it's going to take maybe 10 seconds to do the computation. It's totally parallelizable. This is totally doable. There's no problem. There's no problem going to 100 million dimensional or billion dimensional. That would be possible. The message expansion rate here is 2.88, which is fantastic. If you can get that good message expansion with homomorphic encryption, you're really doing magic. When you start from a naive implementation, you can have 100,000 message expansion rate. So lessons learned. There's many non-trivial ways of improving the performance. When you start from an implementation, it can be hard to know if this is a good implementation or is there how much room is there for improvement. This is something that you just need to be familiar with the stuff and have a lot of experience to kind of understand that and understand what you could possibly do to improve it. Optimizations might not be simple, and it might be difficult to come up with best ways of doing it. When you do complicated computations, doing all these rescalings and getting all of those different parameters and scales to match up can be really, really hard, unfortunately. But we're working on tools for improving that. So that's it.